Alrighty, so the first problems have the graphs with them. And they say to compare the right-hand and left-hand derivatives to show that the function is not differentiable at the point P, find all points where f is not differentiable. So basically, they're giving you a graph, and then we're going to look at it and basically figure out what function makes the left and right-hand side and take the derivative of it to show that they're different. So, number 2... we have basically the two functions are y equals 2 and y equals 2x. So the balancing act here. The left hand derivative is going to be the one coming from the left. Okay, and so this function here is y equals 2, and then this one here is y equals 2x. And so basically we're just going to take the derivative of each of those functions with respect to x and then see what they're equal, and that will then therefore tell us that they're not differentiable at the point. So basically what is the derivative of 2? 0. So y prime is equal to 0. And what's the derivative of 2x? Yep, just 2. And so then, let me see how they want us to write it, just to make sure. I think then they want us to write basically differentiable everywhere except x equals 1, because that's where the point is there. And so that's where the problem occurred. Four is going to include a derivative rule that we don't technically know yet, but it'll be in the next section, so I'm going to go ahead and intro it. It's going to follow the same rules that we normally do. It's just going to look a little different. So number 4, we have on the left-hand side y equals x, and on the right-hand side y equals 1 over x. And so, and the point that we're looking at is 1, 1. So we've got here on the left-hand side, here's y is equal to x, and then over here it changes to y is equal to 1 over x. So y equals x, that one should be pretty easy for us to take the derivative of. We know what that is. Derivative of x is 1. Now this one, this is where you don't know what to do yet, huh?
Do you use like a quotient rule or something?
So, sort of. If there was stuff on top and bottom, we would. But, one, we don't know the quotient rule yet, which technically you don't know the rule I'm about to tell you, but it's a little easier than the quotient rule. So, basically, any ideas another way I could rewrite 1 over x to get x to some power, which would allow me to do something I already know?
You would have to make it like a negative exponent or something?
Yep. So if I rewrite this as y is equal to x to the negative 1, and if there was a number other than 1 on top, whatever that number is would just go in front of it. So this one happens to be 1. And now it works the same way, okay? So what we do is we always bring the exponent out front, and then we subtract 1 from the exponent that's currently there. So this is going to become, the derivative is going to be negative x raised to the negative 2. So then we can rewrite that as negative 1 over x squared
So you want to put it back in. Oh yeah, because you don't want to.
Yeah, and then if you plug in the point, we didn't have to actually plug anything in the first one because they both came out to just be numbers. This one, because we're left with an x, we're now plugging in this point here. Sorry, turn the light off so you can see the iPad and you can turn it back on. So this point 1, 1, 1 is getting plugged back in for x because basically the derivative at the point. So because it didn't come out to just be a number and we were left with an x, we're going to put in 1. It's going to be a process. So this would be -1 over 1, which is just going to be -1. And -1 is not equal to 1, so it's differentiable everywhere except for at x equals 1. All right, then let's see the next thing. We're still given a graph, so this is 5 through 10. And it says the graph of the function over a closed interval D. So basically, the graphs have closed points on the end, so they have endpoints. At what domain points does the function appear to be? We have the first thing is differentiable, the next thing is continuous but not differentiable, and then the last thing is neither continuous nor differentiable. So number 6. Basically what they give you on the graph is y is equal to f of x, which I know doesn't tell you much of anything. But then they tell us that the domain is -2 less than or equal to x less than or equal to 3.
You said what's it asking for?
Do what?
You said what's it asking for?
Asterisk?
No, what's it asking for?
Oh, I was like, did I draw one? It's asking us for where is it differentiable. So here, I'll write it down. And then it's asking us for where it is continuous but not differentiable. And then it's asking us for neither continuous nor differentiable. All right, so the first thing is going to be differentiable, and pretty much the only places that's like not going to be the case is when we have like a jump in like where the graph goes from like up here to like down here, and like being like filled in or not filled in. Anywhere where there's like a hole in the graph, or where we have like, let me go back, any of these things occurring. So it won't have a derivative at like the point, and so it's not differentiable all the way around. So a corner, a cusp, a vertical tangent, or a discontinuity. So
it's just differentiable. This one?
So yeah, basically. So this one, we've got a function that's basically just a curve. I don't see any holes in it, or anything like that. So this one is going to be differentiable on its entire domain. So we're going to say from -2 to 3, including for that. So at all points in the interval -2 to 3. And including because we have the closed circles on the ends of it. And then basically, is there anywhere that it's continuous but not differentiable? Well, we've said it's differentiable all the way.
Mm-hmm.
So basically, there are none, and then neither continuous nor differentiable. Since we've said that on the entire domain it is differentiable, obviously that has to be none as well. I think to avoid having to rewrite the questions, I'm going to just do this one beside. All right, so 8 pretty much gives us the same information. Y equals f of x. Domain is -2, less than or equal to x, less than or equal to 3. So exact same thing there. But this graph looks a little different because we have now it's making a V, okay? And then there is a open circle. It's really hard to see on the screen, but there's an open circle at 3 or at x equals 0, but y equals 3. And then there's a closed circle down here at 0. And then it comes up. There's a hole in the middle of this graph, but it has something to fill it down here at the bottom, and then it keeps coming down and closes at the end. Okay, so this is differentiable where?
X equals -1. Wait, no. Wait, that's...
Or you can tell me where it's not differentiable.
Yeah, sorry. That's what I was trying to say. It's differentiable except x equals -1, and would it be x equals 0?
Yep.
Okay.
And there's one more.
Oh, and x equals 2?
Yep. So this one is going to be differentiable everywhere except for at -1, okay, because basically we've got a corner, okay. Then at 0, because open up here, close down here, and then we also have another opening there, but it does have a dot to fill it. So basically the way that the book will write this, instead of having to do a whole bunch of things like union together, they are going to do this as all points in -2 to 3 closed except, and then they'll do it as x is equal to, what do we say, -1, 0, and 2. So basically they would write it like that, which is obviously completely fine. So then I want to know, where is it continuous but not differentiable? So basically, out of these 3 points that we have removed, because it can't be differentiable, which one of them, or potentially up to all of them, are continuous but not differentiable? Yep. X equals -1 because there's no gap. The problem there is just that there's a corner.
Okay.
So at x equals -1, it would be continuous, but it's not differentiable. That's the only one of those. So then neither continuous nor differentiable would be where?
The other 2.
Yep. X equals 0 and x equals 2. Because if there's a hole, it can't be continuous. So, since we're supposed to spend several days on this section, let's do another one. Why not? Same instructions, but number 10. I just feel like it's good to be able to visualize, because then the more you see it, the more it just will make sense, hopefully. So 10, we have still y equals f of x, which you don't really have to write that down, but, whatever. And then the domain is -3, less than or equal to x, less than or equal to 3. And so, again, so I've got a graph here that has, basically it's going up, then it comes back, kind of makes like a little parabola in the middle, and then comes back down as a line, and it's got end caps. I guess that's, I don't know, whatever. Ends on the on both of them, both sides. So, is this, or where is this differentiable? Peyton's trying to share the wealth.
Fire today.
Missing Josh.
Yeah, exactly.
I have to speak.
You're speaking right now.
Yeah, so just speak the answers.
I mean, the negative 2 and 2 count as corners.
Yeah, either a corner or a cusp. I don't know. One of the two, but yeah. So, are you telling me everywhere but there?
Sure.
Okay, yes.
I mean,
Everywhere.
It's not a corner, it's kind of a smooth line, so.
All right, it's differentiable everywhere except for at negative 2 and 2. So, at all points in negative 3 to 3, except at x equals negative 2 and 2. So then, go back and find the questions. Is there anywhere that it's continuous but not differentiable? So basically, any points that you say except have to fit in B or C.
Oh. So those points. They're continuous, right?
Yes, they are continuous because there's no like holes or anything like that. So they're both going to be continuous, meaning that there are no points that's neither continuous nor differentiable. So that's just going to be none.
Okay.
It's starting to make a little more sense, maybe.
Yeah.
Peyton's got it under control.
It's like the one section Josh isn't here for, I kind of understand, so I can.
Okay,
Finish those questions.
let's see. Let me see. Did I actually give? Oh, okay. So basically these next problems say the function fails to be differentiable at x equals 0. Tell whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. And so essentially we're looking for things that kind of look like these examples that I gave you. So if you're not sure, you can throw them in a graph. Obviously this is like a step function. And so we're pretty much just going to say what's happening in each one. So number 12, scroll all the way down. We have y equals x raised to the 4/5. So even though you might be able to guess based on what we wrote in the notes what that is, I would say not a bad idea to look at a picture because, you know, why not? See what's happening. So x raised to the 4/5. Now, aside from looking at the graph, do you know which type this is?
Well, based on the notes, it looks like it could be a cusp, like raised to something.
Yes. So this one is going to be a cusp.
The graph looks like that as well.
Yeah, So the graph, well, not that you can see it.
Actually, the graph kind of looks like a corner, just not like a very
Yeah.
big corner.
I think if we zoomed in, what we would see is that this is actually arcing
Okay.
here, which is what's making it that way. I'll zoom it in and see what happens. Because sometimes a zoom in will help us see it a little bit better. Maybe a little bit. It kind of looks like it's like coming up and arcing here. You can see it only a little bit better in the graph by zooming it in probably. So that is going to be a cusp. A corner is going to be more straight lines coming off of it. All right. 14. Y is equal to 3 minus the cube root of x. Scroll back and look at our options. Without a graph, what does this look like?
Vertical tangent.
Yeah, looks like a vertical tangent, so we'll just verify.
Wait, how do you do the cubed root again? I forgot how to.
Hit math, and then it's like option 3 or 4, I think.
Oh, okay.
So this graph kind of comes down and then turns and goes the other way, so that's going to be a vertical tangent. Okay, and officially the vertical tangent is basically occurring here where it's like curving and switching and going kind of the other way. So all right, and then this last one might be a little bit of a trick question. The cube root of the absolute value of x. So, if you don't remember absolute value bars, you hit math and then arrow to number, so NUM, and then it's the first option that says ABS. And that'll give you absolute value bars to type it in. So without looking at the graph, what might you have said this was going to be? Because in the notes we had the cube root of x was a what?
Vertical tangent.
Was a vertical tangent. But then we also had the absolute value of x was a what? So this one's kind of confusing because without actually looking at the graph, it would be a little bit hard to tell what it is.
Yeah.
And so looking at the graph, we can tell that it's a what?
Is it vertical tangent? No. Oh. Corner? Oh.
I'm not include.
It's neither of the two that you would think it would be.
Us?
Yeah.
I was like.
I was gonna say that. I was eating food. No one fucking helpful.
That's very polite, Kristen.
You just spit on the ground next time.
No, don't spit on the ground.
You got me spit on the desk. Really?
Oh my gosh.
Now, aside from that, we could also have looked at the descriptions of what we gave for each one and probably have figured out that that was not going to be either a corner or a vertical tangent. But when you can have the graph, why not? Okay. Where are we at time-wise? All right. Now, I think I might be able to get away with not having this book up in my lap anymore. Score. Okay. Find the numerical derivative of the given function at the indicated point. Use h is equal to 0.001. Is the function differentiable at the indicated point? So we're going to be using basically this formula here. So we're going to have whatever a value, now they're going to give it to us as x, I think. Yeah. So basically it's going to be x plus 0.001 getting plugged in for x in the first part of the equation minus, and then we're going to do x minus 0.001 to give us the approximate value for it. So you will end up typing it in your calculator, obviously, because you're not going to know necessarily what something 0.001 is. But then I will also show you how to use the NDER function on your calculator. So, let's see. 18. F of x is equal to 4x minus x squared, and we're told that x is equal to 3. All right, so we're going to be doing, and the first one I'm going to write out like in detail what we're doing, and then the future ones I'm not going to do it that way, but 4 times 3 plus 0.001 minus 3 plus 0.001 squared. So that takes care of the first part, okay? So that's the plus 0.001 portion. Now minus, and then because there's two terms, I would bracket it off. 4 times 3 minus 0.001 minus parentheses 3 minus 0.001 squared all over 0.002. So then basically what I would write from here on out, rather than writing out that step, is I would go straight to this point where 4 times 3.001 minus 3.001 squared minus 4 times 2.999 minus 2.999 squared all over 0.002. So I mainly wrote the first step that I wrote just so that if you go back and look, you can see what the formula was. This was the a plus 0.001 part. This is a minus 0.001 part. So anyways. And then at this point, I would plug it into your calculator because I highly doubt you want to multiply all that by hand. And I would like parentheses off the things that I did when you do it, just so that there's no confusion. Like I would copy it down exactly. And then I would probably do, unless you type it in as a fraction, like with the fraction bar, I would probably do the top, get an answer, and then divide that answer by 0.002. Whenever y'all get an answer, you can let me know.
I got -2.
I also got -2.
-2? Okay. Alright, so -2. And then it asks, is this function differentiable at the indicated point? So, essentially, at 3, is this function differentiable? Now, what is this a graph of? A parabola. So, is there any reason that wouldn't be differentiable? No. So, yes, it's going to be differentiable at the indicated point.
So it's asking if it's going to be differentiable at the x equals 3?
Yeah, because that's the point that they gave us. Let's see. 24. F of x is equal to the absolute value of x minus 3. And again, we have the point x is equal to 3. So this time, I'm just going to jump to this step where I write it as 3.001 and then 2.999. Obviously, if this number wasn't 3, we would have to adjust that, but it happens to be the same. So we're going to have 3.001 minus 3 in the absolute value minus another absolute value, 2.999 minus 3 over 0.002.
Got 0.
Anybody else agree with that? Okay. So then, is this differentiable at x equals 3?
No,
Why?
because it's a corner.
Yep, there's a corner because that graph was shifted over to the right. So, no. There's a corner. You don't have to write why, but just for reference, I'm going to write that. All right, any questions at this point? I think what I'm going to do is I'm going to wait and show you the function on your calculator tomorrow. That way, hopefully, Josh is back and can see it. Because that part's, I mean, not that it's hard to type in, but it'd be a little harder to not be able to see it. And that's pretty much the only thing left in this section, so we'll probably do notes for the next section tomorrow, because I think there's a decent amount. So, but this homework won't be due until Friday.
Okay.
All right, so 1, 5, 7, 11, 13, 17, and 23.